Here's another pressure volume loop, same one we just talked about. But we can ask a question. Well, let's start to ask some questions using this diagram. How much blood is ejected from the left ventricle? Okay, how much blood is ejected from the left ventricle? Stare at the diagram for a second and try and answer that question. Okay, so now that you've thought about it a little bit, let's start to label some more things on this diagram. We can label something called the end diastolic volume, or EDV. Okay, so in this case, the end diastolic volume is what? Equals 125 milliliters, right? So about 125. You could also talk about the end diastolic pressure, right? That would be 20 millimeters of mercury. If there's an end diastolic volume, then there should be an end systolic volume, right? So let's write that up here. NESV, or end systolic volume. In this particular case, it's about 50 milliliters, okay? And these aren't, there's no significance to these values. They're just sort of typical values. So now we can start to answer the question, well, how much blood is ejected from the left ventricle? Okay, we can take the number, the end diastolic volume, 125, subtract out the end systolic volume. So we have 125 minus 50, and that gives us 75 milliliters. Okay, so this volume is referred to as the stroke volume. And I'll just abbreviate it as SV. So SV equals end diastolic volume minus end systolic volume. So why do we care? Why do we care about the stroke volume? It's certainly something we can get easily out of this sort of diagram, but is it useful? Well, stroke volume will actually change. So for example, during exercise, it might increase as the heart is contracting harder. Stroke volume might go down with age or disease. So it's a very useful parameter to try and understand. So let's try and mine this diagram we have for some more data. Let's see what else we can figure out. Well, I mentioned that the time it takes to go around one cycle of this pressure volume loop was 1 second, right? So that means that the heartbeat cycle has a duration of 1 second. So we know that there's 60 beats per minute then, okay? So that's what's called the heart rate. And so based on the heart rate and using the stroke volume, can we talk about cardiac output? So we can ask the question, for example, how much blood is ejected from the left ventricle per minute? Okay? Well, let's answer that question. So we have per stroke, which is 1 beat of the heart, we have 75 milliliters per beat. And we have 60 beats per minute. You notice that the beats cancel out, and then so you multiply these out, you have 4,500 milliliters per minute, okay? So that's a way of judging the flow of blood out, ejected from the left ventricle, which of course is the output of the heart, the systemic output of the heart. And so there's a special name for this. This is called the cardiac output, which is, we can abbreviate as CO. And it's simply equal to stroke volume, SV, times heart rate, which I'll abbreviate as HR, okay? So there's another very important parameter we can get by looking at these sorts of diagrams with the additional information of knowing how many beats per minute there are. What else can we figure out? Well, another very important thing to understand, which we can get derived from this sort of diagram, is called the ejection fraction. So let me just write that down. Ejection fraction is equal to the stroke volume divided by the end diastolic volume. And typically, you might want to represent it as a percentage. So then we would multiply by 100. Well, let's look at our diagram. We have a stroke volume, which we figured out already, as 75 milliliters. So let's put, in this particular case, we'd say 75, and our end diastolic volume we can get from here. It's 125 multiplied by 100. So this turns out to be 0.6 multiplied by 100. That equals 60. Okay, so that's our ejection fraction. And just to give some idea of whether that's good or not, that's about normal. A normal ejection fraction would be about 55%. But of course, it varies between people and so forth. But again, this is something we might want to measure. The ejection fraction will be useful to know. Someone with a very weak heart might, for example, have a very low ejection fraction. A trained athlete might have a high ejection fraction. During exercise, you'll have a higher ejection fraction than when you're resting. One last sort of freebie, very simple thing, but it's a good thing to know, is a thing called the pulse pressure. And this is really quite easy to figure out. It's called the pulse pressure. And that's simply the systolic pressure the difference between the systolic pressure and the diastolic pressure. So you simply simply subtract the diastolic pressure from the systolic pressure. So let's go back to our diagrams. Let's try and figure this out. Well, we said that now this is of course the left ventricular pressures, right? And typically when we measure blood pressure, we're measuring it from the arm. But remember, that's a way of trying to get at what the actual aortic pressures are. But remember again that these pressures, we can almost sort of derive the aortic pressures off of this diagram, even though they're not explicitly shown. Remember the aortic valve opened here, right around 80 millimeters, right? That's shown as this inflection point in the 80 millimeters of mercury. So we know that the aortic blood pressure must be during diastole would be about 80 millimeters of mercury. And then we have the peak blood pressure of about 120. So, and actually during this phase, early on, the aortic pressure lags a bit during this ejection phase behind the left ventricle, but eventually it sort of catches up, and they're very, very close. And eventually, of course, it overtakes the pressure within the left ventricle. But you can assume they're very similar right there at the peak. And so from this diagram, we have 120 as our peak pressure, which is going to be our systolic pressure, and we have 80 for a minimum pressure or during diastole. And so we can simply take these numbers. We take 120 minus 80, and we now have 40 millimeters of mercury in this sort of hypothetical, sorry, it's off screen. 40 millimeters of mercury in this hypothetical person that we're sort of looking at here. I'm going to check the time to see how I'm doing. I've actually gone over time by 3 minutes. Okay. Let me just talk very, very briefly, just to say what other things I would go into next. So I actually planned out, I think, more like a 45-minute talk. But after going through the basics of the pressure volume loop, which I just did, the next topics were to go into active and passive properties. So I would talk about the passive properties, the end diastolic pressure volume relationship and how that relates to the pressure volume loop. Then the active compliance, of course, is related to that. So I talk about compliance. Then I would talk about the active properties, the end systolic pressure volume relationship and how that relates to the pressure volume loop. And I, of course, would mention how both of them are done experimentally by injecting volumes of solution into a heart and looking at these relationships. And then, of course, once you have this a good understanding of how this pressure volume plot works, we can start to doing even more interesting things. So my plan was to go into looking at changes in contractility, how those would affect the things like the stroke volume, the peak pressure, And then, of course, preload is another thing I could talk about, and then afterload. And then, of course, the very last thing in this 45-minute talk that I put together is cardiac work, which is pretty simple. It's just simply the area within the pressure volume loop. But I'll stop there because I've already gone over by 5 minutes.